In this example, I'm going to be doing Coletta problem 521, which is talking about a small mass supported on a vertical spring, and then an additional mass that's 100 grams is attached to the original mass. This causes some oscillations, and then when those oscillations die out, the system is found to have increased in length by 10 centimeters. We know the frequency of the oscillations, and we'd like to find f. All right. So see if you can draw some pictures, tell yourself the story of the situation, and do some analysis and planning. All right, I started my analysis by writing down my goal, which was pretty easy because it ended with find m. So we want to find that mass. And then I felt like this was a particularly important question to get a good mental picture of what's happening. So we started by having a spring that's hanging, and it has this mass m, the one we're trying to find. And we don't know how much the spring is extended from its original equilibrium, so I'm just going to set this place where it was hanging before we put the weight on it as our new equilibrium. So this is where I'm calling x equals 0. Then we put the additional 100 gram mass on it, and that stretches it an additional 10 centimeters. Our delta x is 10 centimeters. So we can think that the force from adding this additional 100 grams is what stretched the spring an additional 10 centimeters. We also know that these two together will oscillate up and down at a frequency of half a hertz. And right away when I have frequency, I like to convert it to period because that's easier for me to think about. And the period of the oscillation is 1 divided by the frequency, so it turns out to be 2 seconds. So that means that this does an oscillation up and back again around its new equilibrium every 2 seconds. All right, so I've got the analysis, and what I really now need to do is figure out a plan that connects the things that I know to my goal of m. Pause here and see if you can come up with a good plan. All right, when I look at this problem and try to make my plan, I feel like this frequency or period is a key part, right? We have an equation for the period of a mass spring oscillator, and it's 2 pi m over k, where m is the total mass connected to the oscillator, right? And we could rewrite that like this, m plus 100 grams over k, and we know t, we know that we have this 100 grams, but we have two missing things. We have the mass that we want to know, and also we need k, the spring constant here. So if only we had a way to find k, this equation would be great for finding the mass. And what's great is we were also given this information about how far the spring stretched when we added the 100 grams, right? We know that 100 grams of additional weight stretches at 10 centimeters, and that's enough information to find k. So first we'll use that to find k, then once we have k, we'll use that in the equation above. All right, see if you can do that. See if you can use this information here to find the spring constant, and then see if you can even proceed then to do the algebra of this step. All right, so for finding k, I start with force equals minus kx, our general force equation for a spring. And in this case, I use this as my equilibrium for x, and then F is any additional force beyond this equilibrium position. So the additional force comes from the weight of this 100 grams, which is here minus 9.8 newtons. Okay, so what I do is I want to solve this for k. K is minus that force to extend it the additional length divided by that additional length. The additional length is 10 centimeters or 0.1 meters. So that's the minus 0.98 newtons divided by 0.1 meters, or k is 9.8 newtons per meter. Where newtons per meter is the right unit, the unit we expect for the force constant for a spring. And then I realized that I wasn't careful with my minus sign here. It's minus the force over x. So that's minus the force, which is minus 0.98 newtons. I also don't really explain why it's force of negative 9.8 newtons. Because what we know is this 100 gram force is bringing an additional negative 9.8 newtons down. But what this is actually the force of the spring. So it might be helpful to write spring there. And so the force of the spring is actually upward and opposite in equilibrium, right? So the spring has to pull upward with an additional 9.8 newtons in order to counter the additional weight of this object, right? So this force of the spring that's additional, so remember there's some force of the spring even at the equilibrium, but then we have an additional upward force to counter this 100 grams, that's 9.8 newtons up, and then given my axis, up is negative in this system. So you want to be really careful about thinking about what's positive and what's negative. Remember, this is the force of the spring when you're thinking about your signs. In any case, spring constants are always positive, so if I'd gotten a negative here, it would have been good monitoring to realize that I'd done something wrong. So then my spring constant is 9.8 newtons per meter, and I want to go to the next part of my plan, which is going back to this equation and solving for m. I want to be careful because I wrote 100 grams in here, but really I want my mass in kilograms because everything else is going to be standard, right? This is newtons per meter, and newtons has kilograms embedded in it. So I'm going to need to be careful and rewrite that in kilograms when I move forward. All right, and the rest is really just algebra. I started up here with t equals 2 pi, the total mass divided by k, and I multiplied both sides by 2 pi. Ooh, I divided both sides by 2 pi. That's the right algebra mode here. To just get, I'm starting to solve for m, right? To just get the square root over here. And then from here, what I did is I squared both sides to get here. Now remember to be careful, if you square something, you square both parts. So this is 2 pi, the whole thing squared. And you'll also notice that 100 grams I put in 0.1 kilograms. I converted it. So then what I'm trying to do from this step is I multiplied both sides by k and then put this on the right hand side, right? And so over here, this is this part multiplied by k. Then I just have to subtract the 0.1 kilogram from both sides, and here I have my formula for mass, my goal, right? Then I just plug everything in here to get my answer. And there it is, 0.893 kilograms, or we only have one sig fig up here in our 100 grams, so we should really write it with only one significant figure, 0.9 kilograms. Now, I want to do some monitoring here, make sure that's reasonable. So this spring was extended initially with some mass, and then we put 100 grams on, and it stretched an additional 10 centimeters, so it makes sense that this was maybe 0.9 kilograms or 900 grams here. That seems like in the range of what's possible. You know, it's not like a kilogram or something crazy that goes on this same spring. I also want to check my units. Since we have here kilograms at the end, this is subtracted from a kilograms. When you subtract two things, you definitely want them to have the same unit. So let's just check that this is in fact kilograms. I did that over here. I have 2 seconds squared. That contributes seconds squared as a unit. Then I have the spring constant, which is in newtons per meter. This is Newton, kilogram meter per second squared, per meter, 1 over the meters. And then what you just see here is that meters cancel with meters, second squared cancels with second squared, leaving me only with the kilograms left. So there we go. I've done my monitoring, and I seem to be good with my answer of 0.9 kilograms for the mass that we started with before the whole thing started oscillating.